Okay, memory hierarchy terminology, use it as much as you can. So we have talked about hit. That means when I want to access a certain level of the memory hierarchy, whichever level you're interested in. If you can find a piece of information you desire in that level, then it's called a hit. And there's hit rate, hit time, miss rate, and miss penalty. And usually the miss penalties are much greater than hit time. If we normalize the miss penalty to the hit time, usually the penalty is 1 or 2 or even 3 orders greater in magnitude, 1,000 times, even 1,000 times greater. Okay, we skip this slide, also skip this slide. Okay, hit rate is the fraction of accesses found in that level, so high that usually talk about miss rate. So if you improve hit rate by 5%, what does that mean? If you improve the hit rate by 5%, that could mean nothing. Maybe from 92 to 97, you don't see big difference. But in terms of miss rate, then it's from 8% miss rate to 3% miss rate. The improvement is more visible. Okay, so sometimes we talk about hit rate, but most often we talk about miss rate. Okay, so the miss rate fallacy, do we want the miss rate to be as low as possible? You want the miss rate of a certain hierarchy to be as low as possible? Yes or no? Under some constraints, then I want it to be as low as possible, but it's not unconditionally as low as possible. If a memory hierarchy never misses, what do you think? Then it must be extremely slow, and you don't want that. Okay? So I want it to miss. Just I want the miss rate to be controllable, to be appropriate. Okay? And miss rate to average memory access time in memory. Okay, as you know, MIPS does not reflect performance directly. Similarly, miss rate does not reflect the average memory access time. The average memory access time is for infinite number of memory accesses. Some may hit in this level, some may hit in lower level, whatever. Eventually, the final memory access time is the time that you really care about, okay? And the miss rate at certain level does not reflect that directly. So what is the accurate equation for memory access time? First, we care about the average of many memory accesses. And then the equation says it's the hit time plus miss rate times miss penalty for a certain level. If you look at all levels or all hierarchies, then this equation becomes somewhat recursive. We talked about that last time. If the miss rate is too low, how can you make the miss rate low? By giving it more space. Right? And if the space is huge, then that thing is slow. You want me to give you an example? Would you like to buy a car whose tank will not need a refill in 3 years? Would you like such a car? Assuming that you use the car regularly, daily, okay? No, such a car won't sell. Okay, 4 questions. Where to place it if it's a new piece of information? How to find it if it's already in there? And if, however, this memory hierarchy is already full, yet a new piece of information must be brought in, which one to replace? And for a write, What should we do? Why is this a question? You tell me. You have to understand the nature of the question before you can properly answer it. Tell me why this is a question. Okay, this is the answer. First, the memory hierarchy is like this. Remember? Who will access to this hierarchy? Human being. Who will access to this hierarchy? Maybe other systems on the internet. Who will access to this hierarchy? Gradually, it's more private to the CPU. How many CPUs are you using in solving this problem? Perhaps not just one, right? Could be 2, 4, okay? So assume that we have 2 CPUs. Then these 2 CPUs are co-working on the same problem. Then they may share the same lower hierarchy, whatever this is. I don't care. You may think of this as level 2, as main memory, as whatever you like, okay? But eventually, information produced by individual different CPUs should converge, should be merged, should be seen by the others in this party. Okay? So whenever you want to write, of course you want to write into this hierarchy, but do you want your peer to know it? Do you? Perhaps you do. So maybe you want to write further down into here. Do you want your friends on the internet to know this? Perhaps you do. Okay? So maybe you want to write it further through into this hierarchy. And your master, the human being, may want to take the file out for some other purposes. Do you want your master, the human being, to have the most updated information? Maybe you do. If that's the case, then write it through all the way down to the bottom hierarchy. Okay? So that's why write may need some further consideration. Because of that, we have write back and write through. Write through is easy to conceive. Write it through. Propagate the result down to all the lower, at least one level down. Okay, so that's called write through. What about write back? This term is not so intuitive. But this term means whenever I want to write, I want to do things fast. So I write only to the topmost hierarchy. I write only to the top hierarchy. I write numerous pieces of new data into there only. How can my peer know that I have new information generated? When does it need it? When it reads it, right? When it reads something, then if I have anything new, I need to reflect that new piece of information to my peer. So whenever I detect a read, I use arrowhead pointing up to indicate it's a read operation. Whenever I indicated someone is doing a read, then I need to update things down to here. Or I can do even more precisely. Whenever I detected a read which reads my new data, then I do the update to the lower level. Okay, so let's see what happens on a read. Whenever it wants to read something, this address will have to be checked by this memory hierarchy. And if there's a match, then that piece of information will have to find a route, or maybe down to here and up, or maybe even down to here and then back up again. Whichever, I don't care. Anyway, that piece of new information will have to find a way to go to there for this CPU. Okay, so now can you see what write back means? Write back means write back on demand or on some special occasion only. Okay, that's the so-called write back. That's where the name comes from. Got it? So that's the write strategy. There's yet another kind of write strategy. Now I'm going to talk about another kind of write. What is this? This is a very precious storage because the space is very limited, only kilobytes, right? So I don't want to waste any bit in this storage. That's the background. And what's happening now is you want to write something. Okay, so if you want to write something, do you need to write it into here, taking up some precious resources? Why such a question? Okay, the reason being, whenever I have something to write, do I still know what I'm writing? Do I still know what I have just written? Yes, the value will still be in the register, right? If I want to use it very soon again, do you think it's smart to write it out and then read it back? Remember, memory accesses are slow. So usually if I want to use it within 10 instruction cycles, 100 instruction cycles, maybe I don't want to reread it again. Maybe I just want to get the contents from my register right away, okay? So a newly written piece of data may not be needed for quite some time. Okay, write something down on your notebook. And then after 10 minutes, if you want to see what you have written down, do you need to look into your notebook or you still remember it? Usually you still remember it, right? So write is similar. After you have written it, maybe for 100 instruction cycles or even more, you still have that piece of information in your register. Okay, so that question is stated below. When I write, and if this write is a miss, do I need to allocate a new location for that write? We just talked about the red question. In other words, how deep should I write it? Now we talk about another kind of question. If that's a write miss, do I need to kick someone out and give it a location? Remember, all the locations are very precious. So we have two options. Number one, write miss with allocation. Yes, I'll give it a location. Number two, write miss without allocation. No, if it's a miss, I don't care. I just skip this level, try to find it in here. If I still don't find it, maybe I also skip this level. Anyway, I'll write to it at a lower level. Okay? So for this top level, it's called write miss without allocation. Okay? With or without allocation. Okay, let's go back to the foil. So now, do you fully understand these 4 questions? Okay, so you fully understand these 4 questions? Let's go on. Okay, where can a block be placed? That is question number 1. Okay. The way you place information in a block can be indexed, directly indexed. Like here. If I have a memory location from 0 to whatever, okay, assuming there are only 32 locations, and for the cache, assuming there are only 8 locations. So 32 locations, every location will have to be indexed by 5 bits. 8 locations, every location needs 3 index bits. In other words, in here, let's use location 4, for example. Location 4 is 100. So in the memory, any 100, don't care 100, any don't care 100, needs to be placed in here, which is called direct mapping. Okay, so whenever the CPU wants to access any of these, how to find it? Go to there. If it's in there, then it's a hit. If it's not in there, then don't bother looking other places for that piece. Impossible, must be there. Okay? This kind of placement is too restricted. Sometimes 0, 1, and 1, 1, 100 are both needed in a very short time interval, so they both will conflict with each other, causing the hit rate to be much lowered. What do? Well, maybe give it more flexibility by assigning 2 to be a pair. A pair, yet another pair, 4 pairs. Okay, 4 pairs in here. So we use only 2 bits for indexing. So for every don't care, 0, 0, if it's to be placed in at this level, it can pick either the left blue location or right blue location, allowing for a little flexibility. Okay, so in such a case, we can have 2 pieces of information with the 0, 0 index coexist in the cache, lowering the conflict a little bit. Okay? But when the CPU wants to look for don't care, 0, 0, it needs to check both places. Want more flexibility? Any memory location can be placed in any of the cache locations. But whenever you want to look something up, you need to check all locations. Tell me which one will have the lowest miss rate. This one. Which one will have the highest search time? Well, if this memory hierarchy is very small, then parallel search is possible. So this will be faster. Because for this kind of arrangement, you need to index it first and then do tag match, 2 steps. Okay? But for this, you can do tag match directly. If the circuit is small enough, how small? Maybe fewer than 100 bytes, then this is the fastest. But for ordinary case, kilobyte memory, this is the slowest. Plus, you need to have a very smart management mechanism because now you have choices. Whenever you have choices, do you have choice this morning? You can choose to skip the class because the lecturer is really boring. or you have studied it fully. You don't need to come, or whatever. Okay, so whenever you have choices, you need to have a smart mechanism. Smartness means complexity, means latency, means area. Okay. So which one do you want to use? Which one do you prefer? Say something. Please. Okay, if you care about speed, then use this. If you care about, what should I say, utilization of the space, then maybe you use this. Okay, there are other considerations. For the cache memory, as you know, memory locations can and must share cache locations. So multiple locations will always be able to map to one. So why don't you think of this as a hotel? Who is registered for this hotel room tonight? Do you know? The only way to find it out is to check your registration book, look it up, and find out, Mr. Wang tonight. Okay, what about 2 nights ago? Somebody else. Okay, so for every location, we need to keep information about who I am. So other than data storage, we need to have tag storage. How big can the tag be? Okay. For this case, I have 5-bit address. I have 3-bit address, so the tag will be 2 bits. Right? For this case, I have 5-bit address here, and I don't have any index or address here, so the tag size will be 5 bits. All address bits will have to be stored. Will have to be written on the registration book. Have you stayed in the hotel before? Ever? Okay. Is the hotel rooms always full? No? No? Sometimes it's empty? Okay. If that's the case, then I need to have an extra bit saying this room has been occupied or not. If it says it's empty, then whatever we have here is nothing but trash. Okay? There always be some information in the circuit. So I need to be able to tell if they're trash or not. Okay. What else? Your hotel is full tonight. But hey, I'm Obama. Vacate a room for me. Can you do that? Who you want to kick out? Who you want to kick out?
Who doesn't pay?
Everybody paid. Everybody paid. So we need to keep some information about how useful this piece of information is, and find the least useful information and kick it out. Okay? So what do you mean by how useful?
When was it last used?
Whatever. Like if this piece is the most frequently used the most number of times, or most recently fetched, whatever kind of information you want, okay? So whenever Obama comes, you'll find someone to replace, okay? And later, Ma Ying-jiu comes, you know Ma Ying-jiu, Do you know who Ma Ying-jeou is, do you? You do. Who is he? Okay, so Obama gets kicked out. Okay, any questions so far? So you understand what's fully associative, what's direct mapped, and what's n-way set associative. Okay, so here I have two-way set associative. Or you want four-way set associative. In other words, you have flexibility in a set. Okay. Do we have three-way set associative? 3 is not a power of 2. Do we have three-way? Yes or no? Raise your hand if you say no. No? 1, 2, 3, 4, you're wrong. Any number of ways is okay. So my next question will be, do we have one-way set associative? Yes? No? Yes, this is one way. Then do we have the max number of ways set associative? Yes, so this is the generic form of any cache organization. I'm sorry, I said that wrong. Cache organization does not have to be restricted to these 3 types. You can think of other cache organizations like what? Like hashing. Have you learned hashing? Whatever is okay, but this is easier. Okay, these are more structured. But any kind of hashing can be used for cache or whatever. Okay. Or better yet, there's another kind of competing design for the cache. Now, I have a CPU. I have a cache. And then suppose I have my memory. Only 2 memory hierarchies. Recently, we begin to use another alternative structure. We put piece of my memory to the nearby location, to a near to CPU location, and access this and the cache memory simultaneously, or even access this first, and if I cannot find it in here, access the cache memory. Okay, what is this? This is part of the main memory. All the accesses to here are deterministic. In other words, according to the address, you know you need to come to here. In other words, whenever you come to here, there can never be any misses. Okay? Yet, this piece of main memory is so close to the CPU, plus it does not need to do tag check. You can never miss. So this piece of memory for the same storage size, the actual storage requirement is less. Okay, circuit is smaller. And the access time is faster, because you don't need to check for validity and for tag match. Okay, so you think this memory is good? Of course, because it doesn't need to do validity check the valid bit, does not need to do the tag match. You think it would be faster? Okay. We have a name for this kind of memory. It's called scratch pad memory. SPM for short. And really, it's just a piece of main memory close to the CPU. or right next to the CPU, similar to the cache. Okay? So whenever there's a CPU access, the access always goes to the cache, but if the decoder finds that the address also points to the scratch path memory, then these access will be nullified right away. And the CPU will get the information right from the scratch pad memory without any hesitation.
How are the blocks copied to the scratch pad memory? What
By memory allocation. Who does memory allocation? Who does memory allocation? OS. Okay? So it's a compiler's job to determine what's to be placed in the scratch pad memory, or by the program itself. The program can copy whatever important information into that scratch pad memory and then use it and never misses. Okay? So many modern systems have both scratch pad memory and the cache memory. And the scratch pad memory has the following advantages. More circuit efficient because there's no need for the tag. Okay? Faster because there's no need to do like validity check and tag match. No placement problem. Always hit. Okay? Less flexible. That's disadvantage. Needs management by the software. Okay, remember I told you the cache memory is all automatic. When I say automatic, by that I mean hardware takes care of everything. Okay, cache, the genuine meaning of cache, of the word cache in English. What does cache mean? Somebody tell me, what does cache mean?
storage?
A cache is a safe place to store food. Okay, and also what's implied is a cache is somehow invisible. If you want to hide food in somewhere, it better be a place where people won't recognize it, won't identify it easily. So it's somewhat like invisible. Okay, so cache is indeed invisible to the programmer, to the program, to the software. Okay, so how is a block found if it is in the in that level? The answer is easy. Okay, so CPU sends an address out. When CPU sends the address out, it's nothing but 32 bits without any implied meaning for any bit. Let me ask you a simple question. If, however, your system has one bad wire, making one of the address bits unusable. Okay, making one of the address bits unusable. If you can choose, do you want the bad wire to be this one, or this one, or the topmost one? Which one will cause you to lose most memory space, memory capacity? Which one will cause you to lose the most memory space? Of course, the less significant bit, right? So if I can choose, I'd rather have a lower order bit broken, right? Every bit will cause you to lose half of the space. Think, am I right? Every bit has the same weighting, have the same effect. Am I right? Am I right? So if you have choice, then nullify this bit, because this memory system is easier to manage. You don't have to skip locations. Okay, if you let these two go out, then your program may need to be rewritten. And very difficult to write your program. And if you want this bit to go out, then you really need to remember very hard which bit that is. Now back to what I want to talk about. CPU sends out an address. The address is a planned 32-bit address with no specific meaning to every bit. When the cache receives this address, cache also sees this address. Okay? When the address arrives, the cache, however, needs to break this 32-bit address into fields. Tell me, what fields do we have? For spatial locality, if memory is byte addressable, 4G bytes. Then what about cache? Cache is not byte addressable usually. The cache is very skinny. Maybe it has only 1K locations, but every location has 32 bytes. So the height is 32 bytes. The height is only byte. Okay? So for a cache, if you look at it from this way, then it's line addressable. If you look at it from the top, then it is again byte addressable, because the CPU sends out byte address. But the refill is line-based if there is a miss. Okay? So whenever I want to refill a cache line, I refill so many bytes. In other words, for these 5 bytes, for these 32 bytes, either they all are in the cache or they all are not in the cache. The only question left is, hey, CPU, which byte do you want? Okay, so the cache will basically not look at these 5 bits first. Then, number of location in the cache is limited. Suppose it's a direct mapped cache. Then for 1024 locations, how many bits do I need to use for indexing? How many bits for indexing? For 1K, cache locations, direct mapped cache. For indexing, 10 bits, right? Right? Which 10? You see, now we know it's 10 bits, but which 10? Of course, these 10, right? Wrong. They can be placed anywhere. And different selection for the index field will result in different cache behavior depending on your application. Maybe you'd rather have your index moved to the left by 2-bit positions. Maybe you even want to have your index split into 2 sections. All are possible. Okay, index bits don't need to be pushed to the lowest order positions. And the rest are the tag bits. Have you seen any cache which does not have index bits? Any cache which does not use any index bits? Have you seen such a cache? Yes or no? Come on, you have 50 chance to be right.
Really not.
Fully associated, we don't need any index bits. Question number 2, have you seen any cache which has no tag bits? No tag bits? Yes or no? That's not a cache. The answer is no. Because why cache is useful is due to its smaller size, right? If it's as big as the main memory, then why bother duplicating the contents and making the initial accesses or misses? No reason for that. Plus, even if you have a cache hit, if the cache is as big as the main memory, tell me, if the cache and the main memory are of the same sizes, which one would be faster, or if the speeds are the same? Which one would be faster?
It's the same because they're relying on the same.
Wrong, the main memory will be faster. Why? Because by definition, for a cache, we need to do validity check, we need to do tag match, forgot. Oh, then I'm duplicating a memory. What's the reason for doing that? By definition, a cache needs to go through all those. Okay? So the cache has to be smaller, so the tag bits are unavoidable. There must be tag bits. Okay, so we have 5-bit line offset or block offset. Both terms can be used interchangeably, cache line or cache block. Okay? We must have these. If it's a must, then I use red. Okay? We must have tags. Sorry. We must have tags. But we may not need any index bits. Okay, so you know that. So you know what block offset means, and the rest will be the block address, and the block address will be further divided into 2 fields. One is index, which can be an empty set, and the other is the tag. Okay. Next question is which block should be replaced on a miss? For direct mapped cache, there's no choice. You have to replace that guy. For set associative, then there'll be options. And the replacement could be random. Just replace anyone. Anyone selected at random. Okay? The real randomness is impossible even for software. So it would be very, very difficult for hardware. How would you implement random replacement in hardware? Well, maybe you just use a counter. Let it run freely. And whenever you need to replace, you just select a few bits from the counter. Okay, always use those few bits. Depending on its current value, you'll do replacement. That's kind of random implementation. Okay, and LRU least recently used. The hardware implementation of LRU is also very, very tedious. If you have 4 candidates, then usually the hardware is already unimplementable, too complicated. So even for complicated CPU like Pentium, Intel Pentium, they have 4-way set associative long time ago. Even for 4 ways, in other words, you have 4 candidates to choose from for replacement. Intel used something called pseudo LRU because the genuine LRU is too expensive. So 8-way LRU is almost just a dream. Okay? And this table shows you as the size gets bigger, the replacement becomes less important. Okay. Significance of replacement can only be seen when the space is limited. Okay, so after cache read-miss, if there are no empty cache blocks, which block should be removed from the cache? We looked at LRU, we looked at random, and for the random replacement, always don't forget to ask, how do you generate the random number? Or how you assure the randomness. Okay, so even for software, even for simulation only, I need to ask those questions. Next, what happens on write? So write through, you understand this already. Write through, all the memory hierarchies have a consistent view of the memory content, so the debugging is easy. And read misses never can produce writes. Why? Because anything in the cache can be replaced right away. Okay? If it's write back, however, a cache line may contain the only latest version. And the other lower hierarchies do not have that version yet. Okay? So the replacement of a cache line will incur the following operations. First, check to see if it's a dirty line. Dirty means it has been written. And then if it's dirty, then I need to write it back to lower hierarchies. So read miss, you want to replace something, and that something to be replaced might incur writes to lower levels. And sometimes we constantly write to a certain location. When do we want to write to that location? Again and again and again and again? When?
The last write.
What?
The last write in the case of write back?
No, I mean one memory location. The program writes to it all the way. Always. What kind of programming style? What kind of problem we're trying to solve? Reduction. Do you know what reduction means? Reduction means I want to add all the elements of an array. Okay? Like when I want to get the average of the class, I need to add your score. What's that? 69. And then add your score, and add your score to the grand total constantly. So that place would be written all the time. Okay? For that kind of program, write-through becomes very inefficient, very, very slow. Okay? So when should we use this? When should we use that? It all depends. No constant winner. Another type of write policy is write miss with allocation or write miss without allocation. We talked about that already. Okay, so for the write-through is so slow that most CPUs use it or don't use it. The answer is most CPUs use it because it makes the system debugging or use of the system much easier. So most people like write-through more than write-back. But the write-through has a deadly shortcoming, speed problem, right? How can you speed it up? Okay, the way to speed it up is first you have to understand the program behavior. Programs usually don't write very often. Maybe write once every 3 instruction cycles. on average. Okay, so since I don't write that often, can I, whenever I want to write through, I write to cache and also try to write to the memory, can I put this write request in the buffer and then continue on with my regular daily work? I don't want to be blocked, okay? And let this buffer, this hardware, to do the subsequent write to memory task for me automatically. If I can do that, then the write through will be as fast as write back, as long as the buffer is not full. So, how big should the buffer be? CPU will not be blocked as long as the buffer is not full. How big should the buffer be? From experimental results, in most cases, 4 locations would be sufficient. Only 4 locations would be sufficient. And this level also needs to write through to the yet another lower level. That level needs to continue on, okay? So every level may have its own write buffer to the lower level. The design detail is all up to you. And if there are 4 into here, maybe only 10%, 5% of these need to be sent into the next level write buffer, although the next level memory is much slower. But anyway, the buffers don't need to be too big. Okay? Why write buffer? Now we know why. So CPU doesn't stall. Why a buffer? Why not just one register? Because sometimes the writes come in a burst. Okay, and then cease for some time, and then another burst. So we need to have a buffer. Read after write hazards and issue for write buffer. So you have the most updated information in here, but not in here. And you said other systems might be doing I/O with you. Is the problem solved? Not yet, but it can easily be solved. Whenever there's I/O request, this request will have to wait until the write buffer empties itself. Okay? And during that time, the CPU may need to be blocked because this communication is not very occasional. Okay, let's go on. Read after write hazards and issue. Yes, so we need to drain buffer before next read, or send read first after check write buffer. Okay, so whenever there's a read, we need to drain the buffer, or that read, we need to go to the buffer and check. Okay, either way is okay. Okay, we have learned cache. Any question about cache? Organization? Replacement? Right? Okay, so usually if I want to give you an exam question, I will use more generic form to test on you. Like if the cache has capacity C bytes, associativity A, and replacement whatever, tell me how many index bits, how many tag bits, how many block offset bits. How to reduce miss rate? Set really what you want? Maybe not. So we need to also reduce miss penalty. Okay? And what about hit? Even for hits, the hit time could be longer or shorter. So how to reduce hit time? What else? Tell me what else. Reduce miss rate is the same as increase hit rate. Missed penalty, hit time, everything else tell me if there's anything else. When I say anything else, then you need to have a checklist. So my next question is, do you know where your checklist is? Where it is at? Where's the checklist? Where is it? It's on page 36, the fourth folio, saying average memory access time is equal to hit time plus miss rate times miss penalty. So everything is already on this page. Okay, nothing's been left out. Okay, so for the reducing miss rate, we can use larger block size. Why? We can use larger cache size. Of course, this is straightforward. And higher associativity, we understand this already. So why larger block size can help? Is this really true all the time? And reducing miss penalty, we can use more hierarchies, inserting an intermediate hierarchy in between, then that can reduce the miss penalty, hopefully, okay? So more hierarchies, okay? And this is only a result of that thinking. And reducing hit time, smaller cache, we already know. But that's not smart, that's too straightforward. So maybe for the hit time reduction, we can give reads priority over writes. Always let read to go first. In other words, we have a cache. There's an unfinished write. Or there are simultaneous reads and writes. Should you let read go first, or should you let write to go first? Which one do you want to do first? Which one?
If you can get the most up-to-date value, then read.
Of course you can. That's the pre-assumption. You want to let the read to go first or the write to go first? Don't pay attention to this. The author may be wrong. Which one first? Tell me why. It's not just tossing a dice. 丢骰子. You need to know why. Why?
So you can continue further.
So the CPU can continue useful work. If that's a read, then usually it means someone is waiting for me home, right? But if it's a write, usually just go away. And no one is waiting for the results. That's why we want to give reads priority. Okay, optimization number 1, the first method. Before I proceed, I need to tell you, cache misses can be categorized into 3 types. Let me erase the blackboard. First type is if we've never used this piece of information before, then the first time we use it, there's got to be a miss, right? That's called must or compulsory misses. First time we use it. The second type is if the space of the cache is too limited, then somebody will have to be squeezed out. And when you need to use it again, it was in the cache but got squeezed out, then that's called capacity miss. The last type is if the cache uses indexing, then pieces of information may be mapped to the same location, causing contention or conflict. That's called conflict misses, even though there are still available spaces elsewhere, but they cannot use those spaces. Okay, so caches have 3 kinds of misses. There's another kind called coherence misses. Let me tell you what coherence miss is as a supplement for now, but later the coherence miss will be one of our topics. Okay, the coherence miss says if I write to this cache If this cache, however, has the same piece of information, a write to this cache, to this location, will cause this piece to be invalidated or whatever. Okay, suppose it's invalidated. Why? Because the information inside is already obsolete, no use. So we simply invalidate that line. Okay, that will cause yet another kind of miss to this cache. That's called coherence miss. Okay, that's the fourth type, to be seen only for multiprocessing. Okay, so for compulsory miss, if you access and cause the miss, what happens then? What happens is you will bring in a whole line of maybe 16 bytes of data. You use only whatever is needed for that instruction. But then subsequent accesses, if it has very good spatial locality, we tend to use these locations, resulting in subsequent hits. Okay, so a larger block can reduce the number of compulsory misses on one hand. But how large? The larger the better? No. If your cache is only that big, then it can contain only a certain number of lines. And if your line gets bigger, then the number of lines gets fewer. Okay? So, using this as the reference point, the possibility of the nearby locations to be needed very soon is high, but then become lower, and even lower. So you don't want your line to be too big. Okay, how to choose proper number of line, proper size of a line is a question. Okay, you need to use proper number of bytes, proper size of the line. Okay, the rest are easy to understand. So let's go to the next slide. Limits of physical addressing. Do you know virtual memory management? Do you know why we need virtual memory? Do you know what to manage? You design your instruction set architecture or design your CPU. Once the CPU is designed, then it has address bus, data bus. Okay, let's just call them address and data traveling on these buses, okay? So what's the size of the address? It's already determined by the CPU design. Suppose the address contains 32 bits. How many accessible locations do you have? 4G, okay? Long time back, this address goes to memory. How big is the memory? Only kilobytes, only megabytes. Today, it's gigabytes already. Okay, suppose it's only kilobytes. But can you ask the programmer to use only kilobytes? The programmer would say, no, I'm eligible to use 4G locations. That's what your user's manual told me. 4G locations, don't tell me it's kilobytes. That's not my problem. And I don't even need to know. Okay, so what do? We use disk or tape to store the whole memory space and use the main memory to talk directly to the CPU. Remember, memory used to be even faster than the CPU. At least their speeds are comparable. Okay, so next question comes, what do we need to put in the main memory? The answer is, a simple answer is the useful information. What do I mean by useful? Well, you know what I mean by useful, by usefulness. Okay, so we have virtual memory manager to handle the page placement and displacement for us, such that the programmer doesn't have to worry about which area of the memory space it's accessing to. Okay? Okay. So traditionally, we call the space that CPU sends out the virtual address. That address doesn't actually exist in the main memory. What actually exists in the main memory are those physical locations. So CPU sends out virtual address, and the main memory accepts only physical addresses. There must be some translation in between. Okay, let's zoom in this area. Okay, after zooming in, we have main memory here, which accepts only physical address, and the CPU sends out virtual address, and there must be some kind of translation mechanism in between. Now there comes in another player called cache. So should the cache use virtual address? Or should the cache use physical address? Which one? Which one? Should the cache use physical address or virtual address? The answer is either. Both will do. If I use physical address, then it's easy to do data consistency between these two hierarchies. However, the access from CPU to the cache will have to go through translation, slowing it down. Okay, so if you're concerned more about speed, then do this. If you're concerned about debugging, then do this. Ease of design. And the translation is always partially not in the CPU. Mostly, I should say mostly not in the CPU, because the translation is managed by this. And this is what? This is a component of the OS. Okay, the OS cannot be in the CPU. CPU and cache? Okay. If CPU and cache are on the same die, is that what you mean? And if the cache uses physical address, is that what you assume?
No, if it uses virtual address.
If it uses this, and this is in the CPU, then this may be completely outside. Maybe. According to what I told you today, even part of the main memory can be in the CPU, the scratch pad memory. The only principle to follow is to make your product competitive. Don't care how you reshape it. Okay, so if there comes a cache, then it can either be physically addressed or virtually addressed. All programs share one address space, the physical address space. Okay, and machine language programs must be aware of the machine organization and know way to prevent a program from accessing any machine resource. Okay, why do we need to mention this? Not very obvious. So just listen to me. Okay, suppose there's one CPU. Suppose there are multiple programs. Each and every program has its own 4G space view. And many programs' address space will need to coexist partially in the same main memory. Okay? So the virtual address, when I say the virtual address is 32-bit, no, in fact, if this is multi-programming, it needs to be more than 32 bits. (32-bit) virtual plus what? Program ID or process ID. Okay, so actually this OS sees an even longer address. Okay, things are getting more and more complicated. Some pieces of information can be made cached all the time. When it's cached all the time, then that portion of the cache is actually used as a scratch pad memory. And some pieces in the memory can be made uncacheable, such as your logs and shared variables. You know what I mean by log? The semaphore? Those things can be made uncacheable. Okay, so there has to be an address translation mechanism in between. Why do we need this? Remember, now we have multiple programs coexist in your system. You have a cell phone. Tell me how many programs are running on this cell phone. Waiting for incoming calls, counting time, and doing this and that. So even for a cell phone, there are multiple programs running concurrently, not to mention a PC. Okay, so there are many virtual address spaces coexist in this system. Okay. Okay, so the address translation should include this part. And then when many of these get translated by the sole VMM. Remember, your system usually has only one operating system. That operating system uses only one VMM. And after the translation by this sole VMM, all the addresses get translated into, say, 20 bits. If you have a 1 megabyte memory, okay, which uses 20 bits for addressing. Okay, you see, different address spaces get unified again because that's the only main memory we have in the whole system. Okay. So do we need protection such that program A cannot contaminate the data of program others? Okay. Are we doing sharing so that everybody gets what he needs? Okay. So the VMM or the address translation should have these functionalities: protection, sharing, and of course it needs to do translation. Three advantages for virtual memory. Translation makes it easy to put the most needed information into here for protection and sharing. Okay, so this is not an advantage really. This is just a must-do. Okay, this is a must-do item, and these are the advantages. And if you must have the third advantage, then I would say the illusion of unlimited, in other words, 4G bytes, fast, in other words, memory speed, memory system. Okay, the illusion to the programmer of an unlimited and fast memory system. Remember what I said. This is not an advantage really. So if you must have the third advantage, what did I say? Illusion of large and fast. Memory system. Okay, next slide. Page table encode virtual address space. Virtual memory system does this. I have disk. On the disk, I have how many pages? How much information, let me say? 4G bytes. And memory, how much information can I store? Maybe 1 megabyte. What's the difference? 4K difference? Okay. Okay, so how do I manage to use this memory to cache? You see, I use the word cache. How do I use this memory to cache information from the disk? For the cache design, I used fixed-sized cache lines. So here I should use fixed-sized memory lines. We give it a special name, page, just like a book. All the pages are of the same size. So if I need to take a page out, put a different page in, it's easy, okay? So we divide the information into pages and divide this area into page frames. Okay, such that every page can be placed exactly into any page frame without any waste. Okay, so a page is just yet another kind of name for a line or block. And the usual page size is from 120 bytes to megabytes. The page size is just like the cache line size. Can be selected. Doesn't have to be fixed. When do you need to have a 1 megabyte page? Huge page, when do you need it? For instance, like for the graphics, every frame is 1K times 1K, which is 1 mega. Okay? And 1 mega page size may fit perfectly for that kind of application. When do you need small page sizes? Basically for the general purpose applications with bad locality, especially spatial locality. Okay? Okay, so 4K, for instance, pages to be mapped to maybe 1K, no, not that many, 128 page frames, okay? This kind of mapping, do you want to use direct, set associative, or fully associative? Which one do you want to use? If you're rich, then you'll say, I want the best, whatever. Okay, so do you want the best?
You can't have fully.
Really? Say that again, and then you're out. Now this time, because OS is doing the work, OS can handle any complexity. I shouldn't say that, can handle complexity to some extent. So fully is not a question. Okay, for software, fully is fine. Yet, whenever I have an additional miss, if I have any additional miss here, then I'll spend billions of cycles, remember? So the missed cost is so high that I want to do my best to try to avoid it. What's the best? Fully associative. What's the cost? Not much more compared with billions of cycles. So even if I spend millions of cycles to handle replacement, it's okay with me. What's the fraction of a million to a billion? Somebody tell me. The fraction of a billion to a million? A million to a billion? The answer is 1 millionth. Not too bad, huh? So software can handle any complexity. Latency is not an issue here. So I use the best way to do replacement or placement. The best way would be fully associative. And fully associative, no equations can follow. Okay, no equations can be followed. No calculation can be done. The only thing I can do is to do recording. Who is where, who is where, who is where. The best way I can do is to do recording. So I have so many virtual pages, which one is at where currently? Either in the main memory or in the disk. Always in the disk, I should say. Okay, so it's a full recording, and whenever I want to access the main memory, where do I find the page? The only way to find it is to look it up in here. You see, so whenever I go to the main memory, I want to look it up in here. Remember in the OS textbook, it tells you if you want to access main memory, then you need to access main memory 2 times. One for page table lookup, and then for the actual access. And however, if you think this page table is too big, too wasteful, maybe only a few pages are used, then maybe you need yet another hierarchy to indicate which pages are currently used, which ones are not. Such that for those not used pages, you don't need to reserve space for them. Remember, there are kilos of these. Okay, in fact, millions of these. The typical address size is 32 bits. Typical page size is 4K bytes, right? So how many pages do we have? 1 million pages. We need to have 1 million such entries. Every entry we need to have validity showing whether it's in main memory or not. Where in the main memory, page address, and the replacement information. And if it's in the disk, where it is in the disk. So the size of every entry is easily over 32 bits. 1 million over 32-bit entries translates into 4 million bytes or more. 4 million bytes are wasted only for storing the page table. That is why we need to save the space for the unused pages. Otherwise, there's no way to put in such a big thing in the kilobyte memory in the 70s. Okay, in the 70s, we already used virtual memory. Okay, got the picture? Okay, so a virtual address space is divided into blocks called pages, and main memory is divided into blocks called page frames. Okay, and a valid page table entry codes physical memory frame address for the page. Okay, plus many, many more. Okay, so a machine usually supports pages of a few sizes. All these sizes are possible. The largest being 16 megabytes for the MIPS R4000 CPU. So this page table is complete. In other words, it does not need a tag. If it's complete, then there's no tag needed. It can be indexed directly. So CPU sends out an address of 32 bits. The 32-bit is seen by the virtual memory manager as containing offset. What offset? Plus page index. Remember how cache controller sees this address? Cache controller also sees an address like this, right? Could be virtual, could be physical. But anyway, suppose it's virtual. How does cache see this address? Also offset. We call this what offset? And then index. And then tag. But here we don't have tag. Here the index may be larger. I'm sorry, the offset field may be larger. Okay, because the page size is much bigger than a cache page. You see, I call it cache page. They all mean the same thing. So by looking it up, I know which pages are stored in which page frames in the main memory or not in the main memory. Okay, details of the page table. If the page table sits here, then it has a valid bit. It has an access right saying this program has the read or read-write or read-write execute rights. Okay? And then the physical address, and also I told you other fields such as for replacement information, such as for location in disk, such as whatever. Okay, so nothing new in here. When the CPU sends out a virtual address, we use the virtual page number to index into the page table and get the translation result out and concatenate this part and the page offset to form the physical memory or main memory address. So page table is huge. It did not fit in the ancient time main memories. What can we do? We use yet another level of page table called page table directory to indicate the page table. Wait, we divide the page table into pieces like 32 page table entries, 32 page table entries, 32 page table entries, and use these page table directory to indicate, yes, I have these 32. No, I don't use these 32. Yes, I need. No, I don't need. And so on to save the unneeded space for the page table. Okay, one more hierarchy. If you use them all, then this becomes wasted, but the overhead is not that high. Okay? Most programs, especially those in your homework assignment, may use only a fraction of a page. But when you run your homework problem, you always similarly will go through all these. Okay, so that's called two-level page table. The purpose of that is to save wasted page table space. So your OS textbook says again, whenever you want to access main memory, you want to access main memory 3 times. In this case, once to the page table entry, to the page table directory, second time to the page table itself, and the final time to get what you want, what your CPU wants. Okay, in that case, then my index field is further divided into 2 fields, one for the page table directory entry, the other for the selected piecewise page table entry. Okay, so page replacement policy. We use some kind of least recently used replacement policy, but the OS will intermittently, for every time interval, clear all these bits. 30 bits mean if the page has been written to. Okay, used bits maybe for the replacement. Whenever it's used. And the replacement will find those 0 marked page to replace. There may be so many candidates. Which one do I choose? Maybe I need more replacement information in order to make decision. So the replacement, I'll leave the details to you, and you don't need to do any reading. You can just use imagination. Okay? Just use imagination so that whenever you read related paper, you know what the author is thinking. Okay, I need to have a free list for the free pages so that I don't need to do replacement yet. Okay, so there's always a free list to make things happen faster. I don't need this because the page table will have another bit saying whether this page is already in the main memory or not. Okay? And in the main memory, the information is packed. Always zeros and ones, whether the page is used or not. So if you go into the main memory, you cannot tell which page is in use. You need to check the page table in order to slowly figure out which page frame is not used right now. Why not keep such a list to make your work easier? Okay? So the use of everything should have a good reason behind it. You should understand the reason. Here, I don't read words to you. I want you to understand. Every time you want to access main memory, you actually need to access memory 3 times. Very tedious, very slow, and every time you found the same translation results because you're still on the same page. What do? Get mad? Or suddenly it comes to your mind that there is a better way to design your system. Since the translation will give me the same output because I'm sending in the same input, for quite some time. Then what if I remember what I'm translating this time? And next time, if I'm doing the same translation, why don't I just use the result I got last time? Okay? So what does it mean? Write down the current translation input and output on a piece of paper. And next time, I look this piece of paper up first. If I get a match, I save a lot of work, right? That's so-called don't do the regular thing. Look aside. So we call that translation look-aside buffer. Got the meaning of the name? Okay. So you want to keep the result of one translation? May not be enough. 2, better. 4, not too bad. Even 6428, not too costly, according to your hardware knowledge. Okay, it won't be a too big piece of circuit. So usually the translation look-aside buffer contains from 16 to hundreds of entries of most recent translations. And very likely your translation can be done in there. So the translation look-aside buffer can have a hit rate of over 99%. So now you understand what translation look-aside buffer is. It's called TLB for short, not for short. This is an acronym. Acronym is not abbreviation. Abbreviation is like trans. Trans is the abbreviation of this word. But this takes the first letters of many words to form a symbol, a term, whatever. Okay, so since TLB is small, fully associative is allowed. Okay, question. If I have a TLB miss, does that guarantee a page fault? Page fault is a bad thing. But does TLB miss guarantee a page fault? It's just like a bullet guarantees a death. Does TLB miss guarantee page fault? Not necessarily. Okay? So TLB mishandling. There's a flow chart saying if there's a TLB miss, what should you do next? What should you do next? You go find a flow chart and try to understand it on your own. Okay, with TLB, we can do this. This is the regular way. With TLB, we can also do the checking here simultaneously. Okay, first we do page table lookup, which is this part. Not first, I mean, we do page table lookup, which is this part, and the TLB lookup simultaneously. Whenever we get information out from the TLB lookup, we abort this operation. No more needed. And the latency of this is much shorter than this. Okay. Or we can do even better. We simply do this first. And if this is a miss, then we go back and do this. It won't wait for too long. This is very fast. Light speed. Okay, so if I use a virtual cache, then I don't need to go through all this. But however, if I use a physical cache, then do I need to do this before cache accesses? If so, can you still guarantee 1 cycle turnaround time? Sounds questionable, right? So for 1 clock cycle or machine cycle, what do I need to do? Now, I need to do TLB translation and then cache access. So I have this TLB translation time in addition. My next question is, can I overlap these times such that I can still use big enough cache? Can I? The answer is maybe, if you are smart enough. Let's see what happens in the cache. What happens in the cache, if this is the time access, what happens is address in, I need to do index. And then I found the cache line which I might want. And then I do tag match. And simultaneously, concurrently, I can read my word. Okay? And if this is a match, then I send the information to CPU. If no, then I send miss signal to CPU. The miss signal to CPU really says, stop the clock or freeze. Okay, don't do anything, wait for me. Okay, the miss signal really only says that to the CPU. Okay, and the cache controller will do the rest, finish things up, and free the CPU for further execution. Okay, so we index first, and then we can begin to reword concurrently with tag match. If that's the case, then can we also do index first while we're doing translation? And when we get the word, when we want to do tag match, hopefully the tag is already available for tag match. You see, I can start my cache operation in the very beginning of the cycle. Okay, so this is under condition that the cache is of the page size, so that the index can be this. Let's look at this address. This CPU address can be divided into 2 fields, page index and offset. And this portion needs to be translated. So if my cache index fall within this area, it doesn't need to be translated, then I can use it right away for indexing. However, if the index also needs to be translated, then I need to wait. Okay? So the condition that I can do this is the cache is of the page size or even smaller. The translation only has to do with my tag, but nothing else. Got it? You see, my CPU address has the untranslated portion and the translated portion. If my index falls within the untranslated portion, then I can use it right away. And this constraint can be loosened a little. Maybe I can have 1 more bit to be translated. And I can use 2 pieces of the cache. 1 piece for one way and the other piece for another way. What am I doing? I'm doing set associative, 2-way set associative. And I use the index other than this unknown bit. I use this n-1 bit index to index both caches. And use the final index bit as my tag. Okay, that will do too. Because half the cache, you see now I have 2 pieces. So every half of the cache only requires that many index bits. Okay, so in fact, I have doubled the size of my cache, but still sticking to only so many bits of index bits. Okay? This idea can be extended to more ways: 2-way, 3-way, 4-way, 8-way, 16-way. In commercial design, sometimes we even use 64-way cache. Okay. Questions so far? Okay, I finished this page. Let's go on. Overlapping TLB accesses. I have finished this page, believe it or not. Okay, so if I use virtual addressed cache, then the problem is sometimes two different virtual addresses may map to the same main memory location. How come 2 different addresses will map to the same memory location? Oh, be aware, one address is in program A, the other address may be in program B, and they're using the shared memory programming model. So 2 programs have different memory spaces, but they actually may map to some overlapped area. So when one program changes the content of its virtual address, and if this virtual address maps to the same physical address as another virtual address of another program, this program may not know that. Okay? And still used the stale data, causing program errors. No, not program errors, result error. The program is perfect, but the result is not what you want, because the communication link failed, and you don't know. We call that synonym problem. Synonym problem is almost the only problem with the use of virtual caches. Synonym problem. If 2 address spaces share a physical frame so that they share the same memory locations for communications purposes. Remember, 2 address spaces, what does that mean? 2 programs, okay? Then there is such a problem. So cache size, block size, if we have a, this is not the right diagram. Let me write you a diagram about that. I have a cache. If the cache size is 1K in units of bytes, 2, 4, 8 in log scale, okay? Is that log scale? Something like that. And if this is the miss rate, okay, for block size, uh, 8 bytes. Okay. If I have a block size of 8 bytes, then it's like this. 32 bytes, then it will be like this. Let me think. For this, and dot, 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 dot. As you can see, for small cache, oh, I'm sorry, wrong. Should be like this. For larger block sizes, if my cache is small, then I will, on the contrary, have higher miss rate. Okay? And when the cache is large, then I have lower miss rate. And for this cache size, my miss rate will, I think I draw the picture wrong again. Should be like this. I'm not sure. You go look this up in your textbook. So there's a best block size for certain cache capacity. Best block size for certain cache capacity. Okay, for different cache capacities, you should choose different block size. And let's look at only one curve. This curve, if it's like this, then what block size should you choose? Maybe I should use different diagram. Okay, if this is like this, and this is like this, I guess somehow messed up. Forget it. But anyway, you know how to choose the right cache block size for the different cache capacities. Okay, so to design a cache, you need to determine on these parameters: cache size, block size, associativity, replacement, write through or write back, and write miss allocation or no allocation. And the optimal choice is a compromise, because all these factors conflict with each other. Okay? And depending on your application, you might have different choices. Plus, if you have structural hazard, maybe you want to use separate caches or dedicated caches. If you mix your instruction and data in the same cache, then we call that unified cache. Okay? So next time when you see unified cache, you'll understand what gets unified. And simplicity often wins, because that results in, first, simple hardware, secondly, speed. And on the downside, its performance may not be that bad. Okay, even on the downside, simple policy may have comparable performance. And the principle of locality helped us design better memory system in the past decades. And this will remain true for the future. And cache misses can be categorized into these three types. And I told you also the fourth type. And write policy, and today's CPU time is a function of all these, not just the CPU inside operation time. And compiler, data structure, and algorithms all can help your memory system to work better or worse. Virtual memory, page table, TLB. And main memory in virtual memory is similar to cache in the cache design. So it's always caching up the lower level, caching up the lower level, caching up the lower level, all the way up to top. When I say top, what do I mean? Do I mean level 1 cache, or do I mean register file? Which is at the top? Do you think it's cache? Raise your hands. Do you think it's register file? Raise your hands. Wrong. Register file is managed by the programmer or compiler. Okay, it has nothing to do with caching, to be precise. Okay, of course you can also argue it's some kind of caching. Okay, so what's the purpose of virtual memory? Illusion of what? Sharing and protection. Okay, these are all the purposes. The purposes can be translated into advantages. Okay, they both are the same.